to have Anton Nahtigal joining us from AVL. He's a senior fluid dynamic and systems engineering analysis engineer, and he's going to take us through. Welcome. He's going to take us through a simulation solution to predict urea deposit formation in SCR systems. Anton is responsible for project work, customer support, technical training in after-treatment components and systems, and his expertise covers SCR systems, exhaust after-treatment system components, DPF failure prediction, so very focused on the topic. And this particular issue is something which is interesting. So thank you for joining us. Go ahead, the floor is yours.
So thank you, Tim, for the presentation and introduction, of course. And I would like to, in the next presentation, explain about the simulation tools which help us to predict deposits formation during the urea dosing injection. So this is the content on presentation. So first I would like to introduce the physical and chemical models which are required for such phenomena to simulate. Then I will move to some examples which is showing the deposit formation, the simulation workflow. So first example is related to the single operating point simulation, and second is the full transient driving cycle simulation, and end up with the summary. Before to enter to the urea dosing simulation, I would just like to give you a brief overlook on the different applications which can be done with the simulation tool. In this case, this is Boost and Fire. So Fire is a CFD tool for fluid dynamic simulation for different applications. Here are presented several possible applications related to the after-treatment application. So upper left animation shows the optimization of the catalyst pipe system. So we know that we have a limited space for placing the catalyst close to the engine, and on one side, on the other side, we would like to achieve good uniformity of the flow in order to increase the durability of the system, performance of the system. So this optimization process runs in a loop. So on one side, we have CAD data, which is parameterized. So let's say the radius of the piping system, and then a simulation solver is needed, which then calculates the uniformity of flow. So value one is ideal uniformity, and then we have set up target to reach this uniformity 0.85, and then finally genetic algorithm is used to optimize the geometrical parameters to reach this uniformity level. So this is one of the possible applications. Another one is DPF, thermal stress analysis. So we know that during the soot regeneration process, the temperature can significantly increase, especially if this is uncontrolled regeneration. In this case, can temperature increase over the material limit, and this is also possible to check with the simulation tool whether if there are some scenarios when the simulation or so the temperature of the regeneration can reach above limited temperature. Then next is SCR dosing process, which we'll later on talk more into the detail. And finally, if we focus on the full system, then typically 1D simulation tools are used. So in this case, the full exhaust line is modeled, including the piping system. Also, the different components can be added for gasoline or diesel exhaust system, and then we can simulate it under different operating conditions, the emission prediction, tailpipe emission prediction. So these are some of the possible applications. Of course, these tools are not only available for the after-treatment application, you can extend to the engine application, to vehicle application. There are numerous of applications which can be done with the simulation tools. So let's move back to the urea dosing process. So why to simulate this process? Urea water solution is dosing is method which is still most effective method for removing the NOx from the diesel exhaust gas. Then simulation allowed to look into the regions, into the process where we cannot do this with some measurement equipment. Then NOx removal process is a part of the strongly transient operating conditions, and deposit formation and ammonia uniformity are the key points for reaching the high performance of the urea dosing process. So deposits depends on the several influencing points. One is the design. So design is not irrelevant where the urea injector is located. So what is the distance between the injection point and the mixing device, or what is the distance to the catalyst? So the type of the mixing devices also have a big impact on the whole process. So all these information are required to put into the system in order to fulfill the simulation requirements. Another important information is injector. So we know that we have a lot of different types of FCR injectors, including the single point or multi-hole injections or air-assisted injectors. All of these injectors have different characteristics. So this means different droplet size, different droplet velocity, and all these factors again have the impact on the urea dosing process. Finally, boundary conditions. We have heard already in the previous presentations that low temperature it's not welcome from the catalyst side because the reactions are not taking place, but the boundary conditions are not only temperature, also the mass flow. So mass flow influence on the interaction between the droplets and the gas stream. So this is another important point, how this interaction takes place. So all these physical phenomena can be covered by the simulation tool, but with some drawback, long simulation time. So for this we need, so I would say, a relatively long simulation time. So we have several methods how to speed up the whole process. One of the possibility is to provide CFD results as pre-simulation to the 1D simulation tool in order to capture also some of the 3D effects in the 1D simulation. So let's move to the what all requirements we need to have, or capability from the software side to be able to simulate such process. One is we need to consider correct properties of the urea water. So these depends on the temperature and depends on the water concentration. Then, as already mentioned, nozzle modeling, so the cone angle, size distribution, and so on. Another is the spray gas interaction. So we need to consider here multi-component evaporation, because if you imagine the single droplet, from the droplet water is evaporated, then thermolysis and hydrolysis takes place in the gas phase. So this is another effect which we need to consider. Then spray wall interaction. So when the droplet hit the wall, there are several effects which we need to consider. So one is the heat transfer between the droplet and the wall during the contact time. Then there are different regimes which needs to be considered. So these are the regimes depends on the momentum of the droplet, the temperature level, and these are regime which decided whether the deposits will take place or not. And finally, cooling of the walls. We have already heard in previous presentation, the temperature is one of the key points for reaching the good performance of the exhaust system. Then moving to the catalyst. In the catalyst, the whole process of conversion, NOx conversion, needs to be simulated. So considering the ammonia adsorption, desorption, then the fast, slow, and the standard DNOx reactions. And in order to simulate the deposit formation, so we need to consider in the wall film model additional kinetic model. So this kinetic model consists of the 15 directions which calculates or basically define which species or which components are currently in the wall film, depends on the concentration of water and other species. So the basic is thermolysis effects, which produce the ammonia as source for the NOx reduction. Then biorate in molten phase, this is considered as a starting point for the other deposits, which are then in the solid state. So this we would like to avoid in our exhaust system. So this is then showing the ammonia urea thermal decomposition as a function of a temperature. So we are distinguished between the low and the high temperature deposits. So all these models, of course, needs to be validated. We have set up with our industry partners the test bench at the University of Graz, where these deposits, wall film formation, are measured. So here we see this test bench. It's considering all these effects which was mentioned before or measured. So the wall film formation under different conditions. So the urea is injected on the plate where the temperature is measured at different location, the amount of wall film as well on the profile of the wall film. So this is showing the animation of such a process. So it's showing the wall film. So here we can see that the wall film is highly transient. We can imagine in the very complex exhaust system, this more or less never become stable. So it's always pulsating injection, then transporting the wall film, and this is a very complex process. So here, next animation shows the measurement of the temperature comparing with the simulation. So left plot shows that comparing the measurement level at 5 different locations during the dosing in the several tens of minutes, and on the right-hand side we see the flow of the or transport of the wall film as well the cooling down of the plate. So these are now the effects which we need to consider as well the validation of the model. So we need to move to the next. This is how to simulate such process. So simulation workflow. In the first case, we are running the steady simulation to reach the thermal equilibrium in the wall. So this is required at the injection start. Then next step is restarting from steady to transient simulation in order to start the urea dosing. At the start of dosing, we are using two technology for speed up the simulation. One is so-called frozen flow, and second is spray database. So what is frozen flow? Frozen flow is before start of injection, all the important equations are turned on. This means momentum, turbulence, energy equation, and the maximal number of iteration per time step is 35 iteration. Then after we reach the steady condition, we are switching off the momentum equation, which leads to the speed up the whole the simulation. And we see on the left-hand side the comparison between the standard approach and frozen flow. It's showing the one segment of the exhaust line, including the mixing device. So we see the flow field, which does not, so basically both results are very much comparable. The plot below shows that the uniformity of ammonia for both different approaches. So we see that in both cases we reach comparable results. Only in the case of frozen flow, the simulation is much faster. Next method which we are using is so-called spray database method. This means that during the first pulse of injection, we store all the droplets into the database. These droplets are then reused each time where the injection takes place. So this means that we are not anymore simulating the dosing, only taking the droplets which are hitting the wall from the database. This is another measure which will speed up the whole process. So let's have a look on the deposition case. So this was, the data was delivered by Volkswagen. So this shows that passenger car exhaust system, it is closed coupled system. So on the left-hand side is the inlet, then is DOC with after DOC is the injection system mounted, and below is then SDPF. So there are no mixing device in this case, and you can see also the some boundary conditions. So here animation shows that on the plate where there is interaction with the droplets, wolfing formation, as well the deposit formation. So this is and the interaction region between the droplets, and you can see that deposits are formatted during the simulation time, which was in this case 600 seconds, which I have to say that this is really long simulation time, which without these measures would not be possible because it would take too long for the engineering usage. So this is now comparison with the experimental data. With one remark, in case of experiment, the dosing was 45 minutes. In case of simulation, it was 600 seconds, because this was still a reasonable simulation time. And this part was then disassembled after it was cooled down. So there is also some time for changing the location of the deposits, but generally we have captured this deposits location with the simulation. Some few words about the performance. Initially, with the original approach of the simulation, we are able to reach about, let's say, for such model, 1 second per day, which is not very much if we need to consider 600 seconds of dosing. So if we are taking into account measures for speed up, then we need to we have a benefit of factor 10. With additional number of cores to run simulation of more on the cluster, we can reach additional speed up. So now with this speed up approach, with increasing the number of cores, we can come to the level where these deposits can be simulated in a reasonable time. So this method was used in case that the boundary conditions are steady. In case that we are working or we would like to simulate the full transient boundary condition, this means full drying cycle, then we can use alternative method. So this method workflow is following. From the boundary condition, we select characteristic points. Let's say low temperature, low high dosing, medium temperature, high temperature, and take the boundary condition for the CFD simulation. After the CFD simulation, we collect the data. These are how much wall film was created, what is the thickness of wall film, and transfer this data to the 1D simulation model, which we can use this for the full drying cycle simulation. So this is the matrix of simulation. So first is the CFD simulation. So we take out the matrix of 9 simulation points with 3 temperature level, low, mid, and high, with 3 dosing rates. And this simulation runs on 80 cores around 1 day. So the simulation model includes the DOC plus DPF, which are used as a pressure drop components. Then there is an injection system, mixing device, which is take out of the system just to show how it looks inside, which takes care for the mixing the ammonia. And finally, then is SCR. So in this case, no chemical reaction was considered in the wall film. The main information coming from the simulation was the wall film evaporation and how much wall film at the end of the simulation exists. So this is then the results for the all 9 operating points. And So we see for the most of the cases, the wall film has been mainly evaporated because there was enough time between two pulses for evaporation. So we have considered 10 pulses. We still see some increase of the wall film, but already after 10 pulses, we consider that we reach quasi-steady solution, which is enough to put this information in the 1D simulation model. So the results from CFD simulation are deposition split ratio. This means how much was directly evaporated ammonia from the spray and how much entered into the wall film. So this is one information. Another is the wall film thickness. So this is part simulation results for the low temperature for 3 dosing, so low, medium, and high. We see that in case of medium and high, some traces of wall film. There are also the type of mixer is swirl type mixer, which creates flow, swirling flow. So this can be also noticed on the wall film, so that there is a pattern of swirl, and also this is the wall film follows that pattern. So next, we move now to the 1D simulation model, which consists of the several exhaust system components. These are the DOC, injector, pipes to consider the heat loss, then SCR and ammonia slip catalyst. So engine out condition has been taken from the test bed. So it was a measured dry cycle. Then injection mass flux. It was overdosed for about 10% over the NOx concentration. Then also the control element was included that switch off the dosing when the simulation or simulation temperature reach below 180 degrees Celsius. And the rest was information was taken from CFD simulation. So someone could ask, what about the points which was not simulated with CFD? So all other points are interpolated. So it is necessary to select really characteristic points which from different temperature level and that make reasonable good accuracy in the case of 1D simulation. So, and then in the 1D simulation, so we can see, so this is simulation time was 60 minutes. So upper two plot shows that deposits formation in milligrams for different wall film thickness. So this can be manipulated by the user. So the thickness amount was taken from the CFD, and then inside the wall film, the user can get information during the simulation how much of each of the component was part of the wall film. We know that some components are more risky for wall film for deposits formation, like biorate or amylite, and some are less critical because they are not stable. So these are then the emission, tailpipe emission. So we see here SCR operating condition are reached after 120 seconds. So this means we have a cold start. We have heard about cold start in previous presentation. So you can see in the below plot NOx at outlet. So you can see that first part there is no difference between inlet and outlet concentration of NOx, so there is no conversion. After the temperature of catalyst reached the conversion temperature, then conversion was started. So the NOx conversion in this case was around 90%. So upper plot shows that ammonia conversion, so blue solid line shows that injected amount. And then dotted and dashed line shows that ammonia coming from either from spray or from the wall film, and then a red line represents the ammonia downstream of SCR. So we have overdosing, so some of ammonia left, and this, what is the excess of ammonia? This is then oxidized in the ammonia slip catalyst. So let's come to the summary. So two simulation approaches has been presented to simulate deposits formation. One approach was focusing on the single operating point with a speed up of simulation to reach to simulate in a reasonable engineering time the possible deposits formation, and also serving as pre-simulation for transient drying cycle simulation. Next workflow was showing for running the simulation in a 1D simulation model, which is real-time capable, and we can model the full exhaust system with all necessary components and predict the tailpipe emission. So thank you for your attention, and